All right, so what I'm going to do today is talk to you a little bit about a series circuit. And I'm just going to move it over here a little bit. There we go. So basically, this is a series circuit. And what we're going to discuss is how to find R total, I total, V, and the voltage drops. Remember, we have Ohm's law circle. Ohm's law circle states that the voltage, current, and resistance are all interrelated. So basically, I drew a circle and I have V on top, I, and R. And if you look at this going across, this will be division, and going across is multiplication. Keep that in mind. So let's go back to the circuit here. We know that this current in a series circuit is the same. That's because the current starts off here, slows down, then picks back up speed, slows down again, and picks up speed again, and returns back to the battery. We call this conventional current flow, because current is going from positive to negative. Electron flow, it goes from negative to positive. So we're going to talk about conventional current flow. That way we don't have to deal with negative numbers in here. So the first thing I want to do in a series circuit is I want to find R total. Well, R total is equal to the summation of all the resistors. So a series circuit is a summing circuit. Very important. We'll talk about that in a minute. So R1 plus R2 plus R3. So if we take R1 plus R2, R3, we get 600 ohms. So if I take the 100, 200, and 300, add them together, I get 600. So the second thing I want to do is find I total. I total basically is the same throughout the circuit. It doesn't matter where I connect the meter. Remember, a meter has to be placed into the circuit. So that means you have to break the circuit and put it into the circuit. So I total, well, I look over my little Ohm's law circle here, and I take I covered up, and I got V over R. So I have to use V total divided into R total. So in this case, what I have is 10 volts, that's my source voltage, divided into 600 ohms. And I come up with 16.67 milliamps. Milli, remember, is 10 to the minus 3. So before we actually get into the voltage drops, a voltage drop, these are called loads. Resistances are loads. So we look at 100, 200, and 300. We know that the 200 ohm resistor is 2 times that of 100, and the 300 is 3 times that of 100. So we should see that this 200 is the value of this R2 should be 2 times that of R1. Likewise, R3 should be 3 times that of R1. So if I want to look at this, VR1, I take I total times it by R1. Remember, R1, I'm going to bring that back down so you can actually see it. There's R1, 100 ohms. So 16.67 milliamps times 100 ohms is equal to 1.67 volts. Likewise, VR2 is equal to I total times R2, and that's 16.67 milliamps times by 200 ohms, and that gives me 3.3 volts. Likewise, VR3 is equal to I total times R3, again, and I get 5 volts. Now, what's interesting on this is that Kirchhoff's voltage law, KVL, Kirchhoff's voltage law, states that if we take the total voltage and subtract it from the summation of all our voltage drops, we should become close to approximately 0 or add 0. It should be about 0. It's going to depend upon how many decimal places we got to go out. So if I do this, I got 10 minus, and I parentheses 1.67 volts plus 3.3 plus 5.001. It's going to give me approximately 0.001 volts. So this is approximately, so it does meet Kirchhoff's voltage law. So again, I found my voltage drops, and remember my voltage drops, your voltage is in parallel, so you do that, and if you measured it, you would see that it would be, you would have the voltage drop. So if we actually look at it, there's the voltage drop, they're in parallel, and they're in parallel. So what I want to do now is find power. So P total, well, there has to be a power wheel we call a power circle. So if we do look at a power circle, I'm going to draw it over here. So P is equal to I times E. E and V are interchangeable. So E is voltage or electromagnetic volts, and I is current, and P is equal to the power. Power is in watts. E is equal to volts, and I is equal to amps. So E is, again, electromagnetic force. So P total, using this equation, I cover up P, I get I times E. So I get I total times it by E total. So I total is 10 volts. 10 volts times it by 16.67 e to the minus 3. I get 166.67. So I get 100, so let me just write that down. So 16.67 milliamps times it by 10 volts. I have 166.67 watts of power. So now I can find PR1. PR1, that's the power through this resistor R1, which is important because if we put the wrong size load resistor in here, it's going to burn up. So let's find PR1. Well, if I want to find PR1, I could do I times E, which is correct. So I could do it that way. So if I know that I take I total, now I can't use E total, I have to use E R1. In this case, I total is 16.67 milliamps times that by ER1, which comes up back up to our guy up here, which is 1.67 volts. So if I take 1.67 times it by 16.667 e to the minus 3, I get 27.83 milliwatts of power. So if I did a 200, and I continue to do this so I can find PR2, using the same equation, 16.667 times it by 200, 16.6, not 200, 16.667 mils. I add times it by the voltage, 3.3. Sorry about that. Gives me 55.55 milliwatts. And then PR3, again, I'm going to take 16.67 mils, times it by my voltage, which is 5.001, gives me 83.35 milliwatts. Now, if I take PR1, PR2, and PR3, so if I'm actually going to do, if I take PR1 plus PR2 plus PR3, when I take those guys and I add them up, 27.83 milliwatts plus 55.55 milliwatts plus 83.35 milliwatts. So if I add those up, I should get a nice number. So let's get that. So I'm gonna keep the mils out just because they're all the same. The units are the same. So plus 55.55 plus 83.35. I get 166.73. So I get 166.73 milliwatts. So if I take a look at what I calculated originally on my power total, does it match up? 166? Yep, it does. A little bit off, but it's really close. That's because of decimals again. All right. So that basically covers how to solve for the powers. But before we actually close this out, let's take a look at this again. Our circuit, let's take a look at our circuit. So we came up with PR1 as 27.83 milliwatts. So we look at this resistor value here. When we look at this resistor value, we want to look at how much power we're drawing. So we're drawing 27.83 milliwatts. So a half watt resistor is way too big for that. Even going down to quarters. So we could go down to even a 1/4 watt resistor on this. So Again, we want to use these values right here to determine the size of the resistor, not the